Good afternoon, students.
Good afternoon, ma'am.
Good afternoon, students.
Good afternoon, ma'am.
Good afternoon, ma'am.
Good afternoon. Okay. So yesterday, not yesterday, day before yesterday, we have seen we have started stability theory. So before going to stability theory, we have seen some preliminaries like basic concepts of linear algebra, like eigenvalue spectrum. Again, how to find eigenvectors and all that. So I give. Whether you finished that homework? I told you to find eigenvalues and eigenvectors of 4 matrices. Eigenvalues, eigenvector and spectral radius. Whether you did it?
Yes, ma'am.
Can you hear me?
Yes, ma'am.
Okay. Okay, so now we will move to the solution of the equation 4.4. This u at t plus 1 is equal to a ut is and u at 0 is equal to u0. I think you can see the screen, right?
Yes, ma'am.
So case 1, when all the eigenvalues are distinct. We will see when matrix n by n matrix A has n distinct eigenvalues. So we are seeing solving equation u at t plus 1 is equal to a ut, u at 0 is equal to u0. So in that case, one is when an n by n matrix A is an n by n matrix has n distinct eigenvalues. If it has n distinct eigenvalues, means it will have n linearly independent eigenvectors, right?
Yes.
It has n linearly independent eigenvectors. So when n by n matrix A has n distinct eigenvalues, or A is symmetrical, so we can say, or A is symmetric. So we have to see how to solve this equation 4.4. So let lambda be an eigenvalue of A. And let U and U be the corresponding eigenvector, corresponding eigenvector for t is equal to 0, 1, 2 and so on, then we have AU is equal to lambda u and A raised to TU is equal to lambda raised to TU, right? If U is an eigenvector and if lambda is an eigenvalue, we know that it satisfies the equation AU is equal to lambda U, right? So what will be A raised to TU? It will be A raised lambda raised to TU, right?
Yes, ma'am.
Then the solution of equation 4.4 can be given by u at t is equal to a raised to t u. A raised to t u, that is nothing but lambda raised to t u. Okay, if we know eigenvalues, then its solution will be lambda raised to t u. And with the initial vector say u. If u is initial vector or u0, you say a raised to t u0. Instead of u0, I am writing u only. Okay, where u is initial vector. So more generally, if u0 can be written as linear combination of eigenvectors of eigenvectors of A, say of the form, say u0 is equal to say b1 u1 plus b2 u2 plus and so on bk uk, where each ui is an eigenvector corresponding to eigenvalue lambda. So this we can write here u0 only, okay, u0. Then the solution will give number 2 to this. Say equation 4.4 we have written, one we will say. Then from 1 or 1 can be written, then the solution of equation 4.4 given by equation 1 can be written as equal to lambda 1 t2 lambda 2 raised to t u2 plus and so on bk lambda k raised to t u k. Is it okay? we know that if A is independent of t in equation 4.4, then its solution is given by a raised to t u0, right? This one, equation 1, a raised to t u0. U0 is nothing but lambda raised to t u0, where u0 is nothing but my initial vector, right? Now since
Yes, ma'am.
sorry, there was a network problem. Can you hear me?
Yes,
Yes,
ma'am.
ma'am.
So up to where we were connected? So whether you up to here it is okay. If matrix has distinct eigenvalues, its solution is given by this one, ut is equal to this. Up to here it is okay.
Yes, ma'am.
So we will see example. Solve equation u at t plus 1 is equal to a times u at t if a is equal to 0, 1, minus 2, minus 3. So already whenever we have to solve such equation, then first we have to find eigenvalues and eigenvectors. Already we have found eigenvalues and eigenvectors of this matrix A in previous lecture.
मॅम स्क्रीन दिसत नाहीये.
नाही
दिसते ना.
दिसते का नाही? मला दिसतंय माझ्या मोबाईलला.
दिसत नाहीये. दिसते मॅम.
दिसतंय का?
नाही. येस.
नाही.
येस मॅम दिसतंय.
Whether anybody has some problem in seeing the screen? Shall I go further?
No.
Yeah. Already we have calculated eigenvalues and eigenvectors of this matrix, right? What are the eigenvalues?
Yes.
Minus
-1,
-1
-2.
and -2. And its corresponding eigenvectors also we have found. So instead of again finding that, I will just directly write let u0 be the initial vector satisfying u at 0 is equal to u0, and as calculated in previous example, recall that eigenvector 1 minus 2 is an vector 1 minus 2 is an eigenvector corresponding to which eigenvalues?
Lambda is equal to -2.
Eigenvalue lambda is equal to -2, and what is the eigenvector corresponding to 1? -1?
-1.
1 minus 1.
Minus
1 minus 1 is an eigenvector corresponding to lambda is equal to -1. Right?
-1 1 है मैम.
Huh? One minus 2 and -1 1 है का?
Yes ma'am.
Where is that? Okay, instead of that I can take k is equal to minus k also, k dash 1 minus 1 लिहिलं काय किंवा -1 1 लिहिलं काय, no problem. K dash is minus K. I can write. Is that okay?
Yes, ma'am.
Okay, so you now we set u1 u2 is equal to b1 1 minus 2 plus b2 1 minus 1. I want to find that values of b1 and b2 which satisfies these values. So what will be this? I can write this as 1 1 minus 2 minus 1 b1 b2, right? Is that right?
Yes, ma'am.
Okay. So the solution what will be b1 b2 then? It is inverse of that matrix 1 1 minus 2 minus 1 and its inverse u1 comma u2. So what is the inverse of this 2 by 2 matrix? What is the inverse? 1 upon determinant of A into adjoint of A. Find out inverse of this. A inverse is nothing but 1 upon determinant of A into adjoint of A. What is determinant of A? Minus 1 plus 2 means 1. What is adjoint? What is adjoint?
-1.
And its transpose. So what will be this? How you find adjoint? Once a cofactor minus 1. Are you there?
Yes, ma'am.
आणि याला काय करायचं 1 2 आहे, so it will be plus and this will be minus, right? So what is the transpose? Minus 1 and 2 and 1. Is that right?
Yes, ma'am.
So inverse is this
Yes,
one.
ma'am.
I will write inverse is minus 1 2 and 1. So u1 u2. So if I simplify, I will get minus u1 minus u2 and this one 2u1 plus u2. So what is my b1? b1 is minus u1 minus u2. And what is b2? 2u1 plus u2. So therefore the solution of given equation with initial vector u0 is given by ut is equal to b1 lambda 1 raised to t what is b1? b1 is minus u1 minus u2. What is my first eigenvalue? Minus 2 raised to t. What is corresponding eigenvector with respect to minus 2? 1 minus 2 plus what is b2? 2u1 plus u2 minus 1 raised to t, and vector is, what is eigenvector? 1 minus 1. So that is my solution. Is that okay?
Yes, ma'am.
So you have to find b1 and b2 constants, not constant, they are vectors only. Okay. So if it is 3 by 3 matrix, then its solution will be b1 lambda 1 raised to t u1 plus b2 lambda 2 raised to t u2 plus b3 lambda 3 raised to t u3. And there you have to find 3 eigenvalues, then corresponding 3 eigenvectors, and then b1, b2, b3 you have to find in this way. Is that okay?
Yes, ma'am. Yes, ma'am.
So one homework. Solve u at t plus 1 is equal to a ut, where a is equal to 2, 2, 2 minus 1. Already you have found eigenvalues and eigenvectors of this matrix.
Yes, ma'am.
So whether they are distinct, what are the eigenvalues?
Yes. Minus 2, 3.
Minus 2,
3.
3. So you can use this method to find the solution. Okay. What about
Yes, ma'am.
B? B matrix 3, 2, 4, 2, 0, 2, 4, 2, 3. त्याचे पण डिस्टिंक्ट आहेत का?
दोन सारख्याच आहेत, एक डिस्टिंक्ट.
सारख्या आहे.
-1, -1, 8.
No, if it is equal, some are equal, then we can't use this. दुसरा 2 by 2 मॅट्रिक्स दिला होता 3, 2, -5, 1. त्याचं
3i.
याच्या आयगेन व्हॅल्यूज काय आल्या b च्या?
2 plus 3i, 2 minus
Minus
3i.
1, 2 minus 3i.
काय?
मॅम ज्या आल्या आता -1 minus 1 8 आणि ज्या आल्या होत्या 2 plus 1 minus 3i.
आवाज येत नाहीये तुमचा. Okay, if it is
2
distinct,
plus
you use
3i.
this method. Otherwise, whatever we are going to, if it is not distinct, then you have to use the next one. Okay, first, okay, at present you solve only one. We will check later. I will give this exercise later. For this, it is distinct, right? So you can use above method. Now everybody know Cayley-Hamilton theorem? We cannot use this method if eigenvalues are repeated. Okay, so we have to use another case 2 when some eigenvalues are repeated. So for that we will require some Cayley-Hamilton theorem and all that. So what is Cayley-Hamilton theorem? Linear algebra. Can anybody recall Cayley-Hamilton theorem? Every square matrix satisfies its characteristic equation. Is this Cayley-Hamilton theorem?
Yes, ma'am.
So take example, verify Cayley-Hamilton theorem for the matrix A is equal to 1, 2, 3, 4. How you will verify what is you have to find its characteristic equation. So find the characteristic equation. What is characteristic equation? Determinant of A minus lambda is equal to 0, right? So determinant of A minus lambda I, 1 minus lambda, 2, 3, 4 minus lambda is equal to 0. What is the characteristic equation? 1 minus lambda,
Lambda square
4
minus
minus
5
lambda,
lambda minus
minus 6 is equal to 0. So this implies 4 minus lambda minus 4 lambda plus lambda square
plus
minus
lambda
6 is equal to 0.
Plus
So this implies
lambda square
lambda square
minus 5 lambda
minus 5 lambda
minus 4 minus 2.
minus 2 is equal to 0, right? This is the characteristic equation. Now we want to verify, means find a square minus 2a minus 2 times I. If it is equal to 0, then we can say that Cayley-Hamilton theorem is verified. So what is A square? Find out A square and all. If A is your this matrix 1, 2, 3, 4. 1, 2, 3, 4 minus 2 times 1, 2, 3, 4 minus 2, 0, 0, 2. If you check, you will get this as 0, 0, 0, and hence Cayley-Hamilton theorem is verified. Is that okay? This already you did in your linear algebra course. Okay, here we have to use what is Cayley-Hamilton theorem. Using Cayley-Hamilton theorem, we have to use different results. Okay.
Yes, ma'am.
So okay, so now we will go to putzer algorithm. This is in the form of theorem. What this says that the solution of equation 4.4 means u at t plus 1 is equal to AUT with initial vector u0 is given by ut is equal to summation I is equal to 0 to n minus 1 ci plus 1 of t mi u0, which is nothing but a raised to t u0, where mi are given by m0 is equal to I and mi is equal to a minus lambda I times I mi minus 1 when 1 less than equal to I less than equal to n. And ci of t I is equal to 1 to n are uniquely determined by equations equation Cn t plus 1, which is equal to the matrix lambda 1 0 0 0 then 1, lambda 2, 0, 0, 0, 1, lambda 3, 0, 0, and then last one is 0 up to here, up to last term is 0, 1 and lambda n, and into C1t, C2t, Cn t. With C1 at 0, C2 at 0, Cn at 0 is nothing but 1, 0, 0, 0. So we have to prove this theorem. This theorem also can be asked as state and prove putzer algorithm. Okay, what this theorem says that the solution of the equation u at t+1 is equal to a ut with initial vector u0 is given by ut is equal to summation I is equal to 0 to n minus 1 ci plus 1 of t mi times u0. That is nothing but a raised to t u0. A raised to t u0 when you will get if all eigenvalues are distinct. If not, then you have to use this another one, summation I is equal to 0 to n minus 1 ci plus 1 of t mi u0, where mi's are nothing but mi satisfies this equation. M0 is equal to identity and mi is equal to a minus lambda I is identity matrix mi minus 1, and CIT satisfies this two equations. Is that okay? We will check now what is mi and how they satisfies this equation. We will prove this in this theorem. So we have to use here Cayley-Hamilton theorem. Proof. So what is Cayley-Hamilton theorem? Every matrix satisfies its characteristic equation. Just now we have. So here this is 2 by 2 matrix, right? Whatever we have verified for 2 by 2 matrix, we have got its characteristic equation is equal to a square minus 2a minus 2i. This character lambda square minus 5 lambda minus 2 is equal to 0. That is characteristic equation. So A satisfies this equation. If it is 3 by 3 matrix, it will satisfy cubic polynomial, right? If my matrix is of order n by n matrix, then its characteristic equation will be n the degree polynomial. Is that right?
Yes, ma'am.
Yes. So from here, what I got here, matrix equation a square minus 2a minus 2 times I is equal to 0. So here a square I can write as linear combination of smaller powers of a. Right here a square, how I can write 2a plus 2i, right?
मॅम
Here
तिथं 5a पाहिजे
5 आहे का? 5 आहे, yes.
a square minus 5a.
Yes, it's 5. Okay, so from this I can write that a square is equal to 5a plus 2 times I. And if it is cubic polynomial, then a cube also I can write as in terms of some constant times a square plus some constant times a plus some constant times identity, right? If it is 3 by 3 matrix, am I right? So by Cayley-Hamilton theorem, we can say that a raised to n can be written as linear combination of a square, a raised to n minus 1 and identity matrix. Is that right?
Yes, ma'am.
By Cayley-Hamilton theorem, whatever may be your matrix, by Cayley-Hamilton theorem, we know that a raised to n can be written as linear combination of identity a square and a raised to n minus 1 if a is n by n matrix. Okay, so it follows that this implies every power of a also can be written as linear combination of linear combination of lower powers of a, right? Identity a square and a raised to n minus 1. So let lambda 1 comma lambda 2 comma lambda n be the eigenvalues of a, not necessarily distinct. Distinct eigenvalues of a. With each eigenvalue is repeated as many times as its multiplicity. Okay, so we are saying lambda 1 lambda since a is my n by n matrix, it will have n eigenvalues, may not be distinct, like, so we are writing say lambda 1 lambda 2 lambda n, where each eigenvalue is repeated as many times as its multiplicity. Now define m0 is equal to identity and mi is equal to a minus lambda I mi minus 1. So give number say equation 1. Then this implies, so therefore by Cayley-Hamilton theorem, we can say that Mn must be 0. How I can say this? What is Mn? I am defining M0 is equal to identity, Mi is equal to this. By here it is given, right? Where Mi is this one. So we are defining Mi is equal to M0 is equal to identity and Mi is equal to A minus lambda I Mi minus 1. So what will be my Mn? What is my Mn?
A minus lambda n times I
A
into
minus
m n minus
lambda
1.
n times I Mn minus 1, right? Now what is Mn
Yes, ma'am.
minus 1? A minus lambda n minus 1 times I Mn minus 2, right?
Yes, ma'am.
A minus lambda n times I, A minus lambda n minus 1 times I. What will be Mn minus 2?
A minus lambda n
N
minus
minus
2 I
I and so on, like Mn minus 3 and so on. So up to where I can go continuing this?
m0
A minus lambda n minus 1 I and so on. So up to A minus lambda 1 times I and last one will be M0. M0 is nothing
m0
but just identity. Okay, if I go on simplifying Mn minus I, substituting the values, I will go up to A minus lambda 1 times I into M0. M0 is nothing but identity only. Is that right?
Yes, ma'am.
So this is nothing but what? Characteristic polynomial. If I simplify this, what will be this? This will give me a characteristic equation. So I can say that by Cayley-Hamilton theorem, I will get this as 0. What is my characteristic equation? If lambda 1, lambda 2, lambda n are eigenvalues A, then what is the characteristic equation?
A raised to
Is these are nothing but roots, na? So what will be
yes, ma'am.
characteristic equation? Lambda minus lambda 1, lambda minus lambda 2, and so on. Lambda minus lambda n is equal
Lambda
to
n.
0. Is that right?
Yes, ma'am.
So Cayley-Hamilton theorem satisfies by Cayley-Hamilton theorem. What I am getting? It every matrix satisfies its characteristic equation. So A minus lambda 1, A minus lambda 2,
Lambda 2,
A minus lambda n.
lambda n equals
If I identity, whatever may be the, is equal to 0, right? So that is nothing but this.
yes.
So therefore I am getting here 0. Is that okay? This 0 is nothing but matrix. This 0 is nothing but 0 matrix, n by n matrix. Is that right?
Yes, ma'am.
So this is the rough part. Or you can say since this is only for the whatever green in green with green pen I have written, that is only for your understanding purpose. If you don't write also, no problem. Okay. Okay, so by Cayley-Hamilton theorem, we say that Mn is equal to 0. Now from definition 1, we have defined M0 and Mi in this way. So from definition 1, we get that a raised to I is a linear combination of M0, M1, M2 and Mi. By definition, since now definition 1 implies that each a raised to I is a linear combination of M0, M1, Mi for I is equal to 0, 1, 2 up to n minus 1. Is that right? See this definition. Mi is a minus lambda I, Mi minus 1. M0 is identity. So each a raised to I can be written as linear combination of M0, M1, M2 and Mi. Right? You can see here. Is that okay?
Yes, ma'am.
Every power of A can be written as linear combination of I, A square, a raised to n minus 1. Right? And Mn is in the form of a minus lambda I. So I can write each a raised to I in the form of or in the linear combination of M0, M1, Mi. Right? And therefore, this implies a raised to t can be written as summation I is equal to 0 to n minus 1 Ci plus 1 of t Mi for t greater than equal to 0, where Ci plus 1 of t are to be determined. Then we can write a raised to t is equal to this one, where Ci, our aim is to find or we have to determine what are that Ci plus 1 of t. Now, we can write a raised to t plus 1 is equal to a into a raised to t. Is that right? I can write like this. Can I write like this?
Yes, ma'am.
Yes.
Yes. Now a raised to t is this one. So what is a raised to t plus 1? Summation I is equal to 0 to n minus 1 ci plus 1 of t. Only I have to replace by t plus 1 mi, which is a times, again a raised to t I am taking as I is equal to 0 to n minus 1 ci plus 1 of t mi from we can give number 2 to this. Say this is my 2. Using 2. Is that okay? Now this, if I take inside summation I is equal to 0 to n minus 1 ci plus 1 of t a times mi, and a times mi I can write as mi plus 1 plus lambda I plus 1 mi using 1 using 1. Is that right? How I can write a times mi? Mi is nothing but a mi minus 1 minus lambda I times I mi minus 1. So what will be a mi? Mi will be a times mi. I can write like this using or from 1 or using 1. Can I write like this? A times mi writing using equation 1. Is that okay?
Yes, ma'am.
Now I will simplify this. Which can be written as summation I is equal to 0 to n minus 1 ci of t mi n minus 1 ci plus 1 of t lambda I plus 1 into mi. Can I write like this? Can I write like this? What if I simplify this? Summation I is equal to 0 to n minus 1 ci plus 1 of t mi plus 1 plus lambda I plus 1 mi. But in first summation, I have replaced I by I minus 1. If I replace I by I minus 1 and used the fact that m is 0. Is that okay? What was this? First sum is what? Summation I is equal to 0 to n minus 1 ci plus 1 of t mi plus 1 plus second term is as it is I is equal to 0 to n minus 1. Second term we are not changing. that okay? Now for sum, in this sum, replace I by I minus 1. Replace I by I minus 1. If I is equal to 0, what will be next? Say j is equal to I minus 1, I am saying. So j will start from where to where? Are you getting this? I am replacing I by I minus 1. So if I starting from 0, I minus 1 will start from याला तुम्ही j म्हणा. Say j. So where j will start from? When I is equal to 0. J will be what?
-1.
I will start from one of these.
-1 to n minus 1. I am replacing I by I minus 1. If I is 0, my new will be minus 1 to 1. 1 to n minus 1.
1 to n summation I is equal to 1 to n. This will be I plus 1 becomes t of t and mi. Is it okay? I want I minus एक टर्म पुढे जाईल ना. मी सबस्ट्रॅक्ट करते म्हणजे माझा जो इंडेक्स आहे 1 2 is it right? And it will n minus 1 आहे इथे होईल. So ci of t mi. And this is there okay? N is 0. So last term and as mn is 0.
मॅम स्क्रीन दिसत नाही.
So this summation is equal to 1 to n ci of t mi will reduce to, I can write this as I is equal to 1 to n minus 1 ci of t because
Ma'am,
last
दिसत
term is
नाहीये.
0.
मॅम स्क्रीन दिसत नाही.
दिसत नाहीये मॅम.
मी आता लिहिते डार्क ग्रीन पेन लिहिते मी. Can you see the screen?
No, ma'am.
No, ma'am.
दिसते मॅम.
दिसतंय का आता? Due to slow network, I think I use now landline, BSNL landline also. But, there was also, it was showing bad network. Now I am using mobile network, Airtel network also, it is showing the same thing. Poor quality, call quality. You can't see, I think. I am scrolling the screen. Give you this number, equation 3. Is satisfied. आता दिसतंय का? मी रेड पेन लिहिते.
नाही मॅम, दिसत नाही.
नाही दिसत मॅम.
CIT 1 to n are chosen to satisfy the system. And this होतं ना? Okay, I will read it. Just only 2 lines are remaining. हे दिसतंय का तुम्हाला इक्वेशन 3?
नाही मॅम.
Okay, I will share this PDF to you. I think there is some problem.